In the previous video, I just covered what KEQ is, and now in this video, I'm going to explain what Q, the reaction quotient, is, and also work a sample problem for you. So in a simple basic reaction of A going to B, we, in the last video, determined that KEQ is equal to the concentration of B over the concentration of A at equilibrium. Remember, equilibrium is just a state in the chemical reaction where for every one molecule of A that converts to B, one molecule of B converts back to A. Okay. So what is Q? Q is actually the same equation where you're looking at the relationship of the concentration of products over the concentration of reactants. So the concentration of B over the concentration of A. But instead of at equilibrium, Q is looking at a reaction at some moment in time. Okay? Q will usually be very different than KEQ when you're just looking at a snapshot of the reaction. Okay? So for example, we're kind of applying this to our body chemistry. When you have kind of just woken up from sleeping, your body is at some type of equilibrium where you haven't really eaten much in the past 8 to 10 hours or so, and so your body is at some new equilibrium. You wake up and you eat breakfast, and all of a sudden now you have this influx of biomolecules from your breakfast. You've got proteins, you have lipids, you have carbohydrates coming in, and all of those molecules have to be processed by your body. So you, at that snapshot in time during breakfast, have completely just like ramped up a lot of chemical reactions, right? You've adjusted the amount of products and reactants that you have in your body. So that's where, for example, you would use Q. So again, Q is a snapshot in time of a reaction that is occurring. Okay? So usually what we'll do is we'll compare KEQ to Q. Okay? So if KEQ is equal to Q, that means that you're actually at equilibrium. And that makes a lot of sense because if the reaction quotient Q is equal to KEQ, that just means you're at equilibrium, right? They're the same number. The ratio of products to reactants is the same, so you're already at equilibrium. But that's usually not going to be the case, right? Right after you eat breakfast, you're not at equilibrium. You've just now influxed a whole bunch of substrates for your body to work on, or some reactants for your body to work on. So what happens if What happens if Q is greater than KEQ? See, so if Q, the value of the ratio of our products to reactants of Q is greater than KEQ, what does that mean? Does that mean that the reaction will proceed forward or the reaction will proceed in reverse? So if Q is greater than KEQ, that means that you likely have too many products, right? Because our products are really, really high. So we've got too many products. So that means that the reverse reaction will be favored. So reverse reaction favored. Okay. But what if Q is less than KEQ? So if Q, our value for Q is less than the actual KEQ, that means that we probably have too many reactants, so the forward reaction will be favored. All right, so in the unlikely event, if KEQ is equal to Q, that means you're already at equilibrium. You're at equilib. If Q is greater than KEQ, that means you have too many products, right? You're heavy on the product side, so the reverse reaction is going to be favored. So B would convert back to A. And if Q is less than KEQ, that means that you likely have too many reactants, and so the forward reaction will be favored, where A is going to be converted into B until you get to that ratio, right? That's the equilibrium ratio, or KEQ. Now this kind of ties into a principle that's also mentioned in your book. It's the Chatlier principle. So if we think of some reaction, maybe A plus B goes to C plus D, there are ways that you can poke and prod this reaction to make it go forward or make it go reverse. So kind of like when I mentioned about breakfast, when you eat a lot of breakfast, or when you eat throughout the day, essentially, you're adding a whole bunch of reactants to your body. So the body chemistry that's occurring is going to essentially push the reaction forward. And the reason it's going to go forward is because you've just tweaked the Q value for that reaction. So Q is actually going to be less than KEQ, so the forward reaction would be favored. So if you add reactants, that favors a forward reaction. Also, if you add products, so it's possible that some vitamins could be on the product side of an equation. So if you take a vitamin supplement, then maybe you've added a bunch of products. So what might happen is those vitamins might break down into their smaller starting pieces, and your body would use those differently. So if you add products, you'll actually you'll push the reaction to the left and favor the reverse reaction. And this is that idea of Le Chatlier. So if you add reactants, you're going to push the reaction forward to make more products. And if you add products, you're going to push the reaction backwards to make more reactants. Okay. Same thing occurs if we're not adding stuff, if we take away things. Okay. So let's say that D goes off and gets siphoned off into some other biochemical process in your body. So you're essentially decreasing the concentration of D in this chemical reaction. That's going to drive the reaction to move forward to make more D. Okay? So if you remove products, it's going to drive the reaction to go forward to try to make more of D so it can be back at that equilibrium, right? Have that proper ratio of products over reactants. And also conversely, if you, A, for whatever reason, got siphoned off and you were essentially decreasing the amount of A available to this reaction, that's going to drive the reaction in reverse and have C and D combine and break back down into A and B. Okay, so that is the idea of Le Chatlier. So let's work a sample problem with K and Q. Okay, so high fructose corn syrup is produced from the conversion of glucose into fructose. So, and this occurs via an enzyme, not in your body, but it's found in nature. So if you want to make high fructose corn syrup, you'll convert glucose into fructose. Oops, sorry. All right, so the K for that reaction, the KEQ, is equal to 0.74. Off the bat, what does that tell you about this reaction? Are products or are reactants favored? And hopefully, since the number is less than 1, you can say that the amount of reactants is larger, so you have a bigger denominator, right? So we have fructose, I'm just going to say FRU, over glucose, glue, right? So if the number is less than 1, that means that you have a bigger amount of reactants, so the denominator is a larger number, right? So my question I would ask to you, and this is kind of looking at what question 2 at the end of the chapter, is if the system is at equilibrium and glucose is 0.22 millimolar, what must be the concentration of fructose? So if we're at equilibrium and the concentration of glucose is 0.22 millimolar, and remember milli is -3, so I could just go ahead and write E -3 molar, what is the concentration, which I'm going to call X, of fructose? So this just seems like a pretty straightforward multiplication issue where we're going to take our, let me get my highlighter here. We're going to take our value here in molar and multiply it by our equilibrium constant, and that'll give us X. So you can crunch those numbers and solve for X that way. But what if the other question was, if you have a mixture of glucose and fructose, and the concentration of glucose is equal to 1 molar, and the concentration of fructose is equal to 2.8 molar, which way will the reaction proceed? So that would be, would the forward reaction be favored or the reverse reaction be favored? So this is an example where 1 molar and 2.8 molar are giving us a snapshot in time of that reaction. So we must calculate what is the Q for that and then compare it to the KEQ. And remember, Q and KEQ have the same formula. So Q is equal to the concentration of fructose, sorry for that line there, over the concentration of glucose. And in our snapshot values, right, fructose is 2.8 molar and glucose is 1 molar. So our Q is 2.8. So now we have to compare our Q value of 2.8 to 0.74. 2.8 is larger than 7.4. So if Q is larger than the KEQ, that means I have too much product, so the reverse reaction is actually going to be favored. So fructose is going to convert back into glucose, so I can, until it reaches a ratio of fructose over glucose of 0.74.